So welcome to this lecture. Now in oscillations topic, it is important topic. We will take three types of questions: multiple choice questions, then multiple select questions, and numerical ability test questions. So in this lecture, we will see some introduction of oscillations. In this lecture, we will see introduction to oscillations. Then we will take some objective type questions. Then we will go for composition of SHM as well as angular SHM. Then multiple choice questions on that, and then we will take multi-select questions and NEET questions. So first we will start with introductory part of oscillations. So here, if we say what is an oscillatory motion? Any motion that repeats itself after equal interval of time. Interval of time is called periodic motion. So here, any motion that repeats itself after equal intervals of time is called periodic motion. So if we see example, now here some body is moving along circular path and it is continuously moving. So motion is repeating, means suppose we take point here, suppose point A. So what happens, body starts from A, it comes again at A, then it goes and then comes at A, goes from A, comes at A. So this is periodic motion, and time required to complete one that motion, that is called periodic time. So this is periodic motion. If we take here, this is also periodic motion. It is repeating itself. It is repeating itself. If we take, this is also periodic motion. This is also periodic motion. So I have shown you three different motions, and all are periodic motions because they are repeating after certain intervals of time. Then what is an oscillatory motion? If an object in periodic motion moves back and forth over the same path, the motion is called oscillatory motion or vibratory motion. Now here we have some examples. Now if we see here first example or this example. So here particle is moving along this direction as well as along this direction. So it is to and fro motion, back and forth motion along the same path. Here also to and back and forth motion along the same path. Here also it goes like this, it returns like this. So these motions are oscillatory motions. But if we see this motion, what happens here? If we take any point, suppose here P, particle goes in this direction. It never comes back along backward direction. So this is not periodic motion, oscillatory motion. Not oscillatory motion. This is also the particle, it goes like this, always like this. It does not come back along the same path. So it is also not oscillatory motion. So see here, every periodic motion, every oscillatory motion is periodic. But every periodic motion may not be oscillatory motion. So here this first one is periodic, second one is periodic, but they are not oscillatory. While this one and this one, they are oscillatory motion. They are periodic as well as oscillatory motions. Now if we take simple example, if we take spring mass system. So this is a horizontal spring, here it is fixed and another end is attached to block of mass m and here it is frictionless surface. And we have attached spring mass system like this. Now when we do not apply any force or anything, it will remain at rest. That mode is called relaxed mode. And this position x is equal to 0, we will call it as equilibrium position. Equilibrium position. But suppose we extend that, means we move that mass towards right side. What happens here? It is displaced through x. Such a motion is called extended motion. So what happens in this case? Force will act. F is force. Force will act towards equilibrium position. Equilibrium position. Now if we compress that spring, if we move mass towards left, so here what happens? Minus x we can take displacement. Now here also force will act, and that force is towards equilibrium position. This mode is called compress mode. So if we extend or if we compress, energy stored in the spring, and if we release, that spring mass starts oscillating about equilibrium position. So what happens here? We know that for an ideal spring, the force related to the displacement by F is equal to minus kx, means force is proportional to the displacement and opposite in sign. It is called simple harmonic motion. It is called simple harmonic motion. Means force is proportional to displacement and opposite in direction. Means when we extend, force will be towards equilibrium position. So if we move mass away from equilibrium position, force will act towards equilibrium position. So such a motion is called simple harmonic motion when force is proportional to displacement and opposite to the displacement. So when that mass is moving along straight line, that motion is called linear simple harmonic motion. So when the force acting on the particle is directly proportional to the displacement and opposite in the direction, the motion is said to be linear simple harmonic motion. Motion is said to be linear simple harmonic motion. So when the force acting on the particle is directly proportional to the displacement and opposite in direction, the motion is said to be linear simple harmonic motion. So we write here F is equal to minus kx. Now according to Newton's second law, we know force is equal to mass into acceleration, d2x by dt square. So this is according to second law. So we will get differential equation. M d2x by dt square plus kx is equal to 0. Then we can write here d2x by dt square plus omega square x is equal to 0. Means we will divide throughout by m. So we will get m here. M will go, and this k by m, it is written as omega square. That is constant. K is called spring constant. So k is equal to m omega square and omega is equal to under root k by m. And here this equation, this is second order linear and homogeneous differential equation. It is second order linear and homogeneous differential equation. And if we solve, this is very simple to solve. If we solve this, x is equal to, we get a sine omega t plus phi, where this omega t plus phi, this one, is called phase of the oscillations, and phi is called epoch. Epoch means it is also starting phase. Starting phase means phase at t is equal to 0, time t is equal to 0. Now omega t plus phi, it is called phase, means it decides x at time t. And we know sine function, it varies between +1 and -1 through 0. It varies between +1 and -1 through 0. So what happens? X will vary between plus a and minus a through 0. So this a is called amplitude of oscillations. So see here, if we take this spring mass system, somewhere here you will have equilibrium position, x is equal to 0. It will go maximum here and maximum here on this side. This is plus minus a, this is plus a. So in this way we get, this is called simple harmonic motion, and this is linear because it is along straight line. Now from this we define certain quantities. So the displacement of particle from equilibrium position is given by this. X is equal to a sine omega t plus phi. Phi is called starting phase. Now a and phi are determined by uniquely by the position and velocity of the particle at t is equal to 0. So what is position of the particle at t is equal to 0, and what is velocity at t is equal to 0? That decides a and phi. Now here, if t is equal to 0, and if the particle is at x is equal to 0, what is meaning of this? So you suppose particle is moving along x-axis. Here it is x is equal to 0. Here x is equal to plus a, and here x is equal to minus a. So this particle, it is moving along this path, to and fro motion. So if at t is equal to 0, particle is here, at x is equal to 0. So if we use here 0 is equal to a sine phi, because t is 0. Now a is not 0. So what happens? Sine phi is equal to 0. This gives you phi is equal to 0. That is starting phase. So it is, when phi is equal to 0, it starts from equilibrium position. But if particle starts from this one, from equilibrium position at t is equal to 0, what will happen? So at t is equal to 0, x is a. So a sine phi. So what happens here? Sine phi is equal to 1, means phi is equal to pi by 2. So when particle starts from extreme position, this is called extreme position, phi is pi by 2. When it starts from minus a, phi becomes 3 pi by 2. So like this. So the phase of the motion is the quantity omega t plus phi, and x of t is periodic and its value is same each time omega t increases by 2 pi. So when omega t increases by 2 pi, means here see, x is equal to a sine omega t plus phi, and suppose we take here a sine omega, and time is increased by so omega t, it is increased by 2 pi omega t plus phi. This is equal to a sine omega t plus phi. So after omega t is equal to 2 pi, you will get the same one. So here, so t is equal to 2 pi upon omega, and this is called periodic time. So t is equal to 2 pi upon omega is called periodic time. So here equations of SHM. X is equal to a sine omega t plus phi. The velocity is what? These formulations already known to you. So v is equal to dx by dt. If we differentiate that x, we will get x is equal to a omega cos omega t plus phi, or v is equal to omega under root a square minus x square. Because this one I can write, we know cos theta, cos square theta plus sin square theta is equal to 1. So we can write cos square theta is 1 minus sin square theta. So cos theta is root of 1 minus sin square theta, and using this here you can get this. So v is equal to omega under root a square minus x square. Now see here, suppose particle it is moving between plus a and minus a through 0. So when x is equal to a, what is velocity? 0. When x is equal to minus a, velocity is 0. What is velocity here? X is equal to 0 at equilibrium position. V is equal to omega under root a square minus 0. So square root of a square, omega square root of a square. So you will get here velocity it is plus or minus a omega. Plus means along positive direction. Minus means along negative direction. So in simple harmonic motion, that negative sign gives you direction, or positive sign gives you direction. So here a omega, that is maximum velocity, and that velocity it is at equilibrium position. It is at equilibrium position, and that is a omega. So the velocity is 0 at extreme positions and maximum at equilibrium position. And now see here we have x is equal to a sine omega t plus phi, and suppose velocity is a omega cos omega t plus phi, and suppose we take phi is equal to pi by 2. Phi is equal to pi by 2 means here we will get what? X is equal to a sine omega t plus pi by 2, and at t is equal to 0 we get x is equal to a sine pi by 2, and sine pi by 2 is 1. So a, so it starts from extreme position. So what is the graph? So you will get graph like this. So particle is oscillating between plus a and minus a, and you will get graph. This is displacement time graph for simple harmonic motion when phi is pi by 2. When phi is 0, then you will get graph. It will start from equilibrium position and you will get graph like this. When phi is 0. Now what is velocity? So velocity what? At t is equal to 0, v is equal to a omega cos phi. Now for phi is equal to pi by 2, cos phi is 0, so v is equal to 0. So velocity will be 0, starting velocity. So graph for, now see here, if we take here this maximum to this maximum. So what happens here? Plus a to plus a, one cycle is completed, and for that cycle we require time t. This is called periodic time. This is called periodic time. Now this is also periodic time from x is equal to 0 to x is equal to 0. In same sense, means here from this point x will increase, from this point x will increase along positive direction. So same point. So phase is the same. So here also this is periodic time. T is called periodic time. Now if we convert that into omega t, if we convert axis into omega t, means multiply t by omega t. So what happens? We get these points. So this point is pi by 2, 3 pi by 2, 2 pi, 5 pi by 2, 3 pi, 7 pi by 2, 4 pi, and so on. So we have converted that time axis into angle axis by multiplying omega. And this omega is called angular frequency. Is called angular frequency. So here now, in place of t, we have omega t. In place of t, we have omega t. And now, what is value of omega t? 2 pi to 4 pi means omega t is equal to 2 pi. Here also 7 pi by 2 to something you will get there. So that is also 2 pi. So omega t is equal to 2 pi. So the period of oscillation is t is equal to 2 pi upon omega. 2 pi upon omega. Now see here, this is velocity. This is velocity of the particle. And we have already seen at t is equal to 0, velocity is equal to 0 because we have taken phi is equal to pi by 2. Now, if we see here, peak of velocity and peak of displacement. Here, peak to peak. So, velocity and displacement are not simultaneously maximum or simultaneously minimum or simultaneously 0. So if we take omega t axis and if we compare that angle difference between maximum of displacement and maximum of velocity here. So here 5 pi by 2 minus 2 pi. It comes out to be pi by 2. Here also it comes out to be pi by 2. So that's why the phase difference between velocity and displacement is pi by 2. It is pi by 2. Now we'll go to the period of SHM is defined as the time taken by the oscillator to perform one complete oscillation. After every time t, the particle will have the same position, velocity and the direction. So t is equal to 2 pi upon omega, we have already seen. So t is equal to 2 pi under root m by k because omega is equal to under root k by m. Under root k by m. Under root k by m. Now see here, if we see equation t is equal to 2 pi under root m by k. So t is proportional to root of m when k is constant and t is proportional to 1 upon root of k when m is constant. So if we take same spring and if we go on changing mass, if we go on increasing mass, period will go on increasing. Period will go on increasing. But suppose if we take same mass, but if we take different springs having different force constants k, and if k is increasing, period of oscillation is decreasing. Period of oscillation is decreasing. So suppose if we plot graph of t versus m, then we will get graph like this, parabolic graph. But if we plot graph of t square versus m, so if we take t square, it is proportional to m. Then we will get straight line graph like this. We will get graph like this. Now next one, the frequency represents the number of oscillations that the particle undergoes per unit time interval. So the inverse of periodic time is called frequency. So f is equal to 1 upon t, frequency. 1 upon t is equal to omega upon 2 pi and it is in hertz. So f is equal to 1 upon 2 pi under root k by m. So when k is constant, m is more, frequency will be less. And omega is called angular frequency and its unit is radians per second. So t is equal to 2 pi under root m by k, f is equal to 1 upon 2 pi under root k by m. The frequency and period depend only on the mass of the particle and force constant of the spring. They do not depend on the parameters of motion like amplitude of oscillations. The frequency is larger for steeper spring, means large values of k, because if we see frequency here, it is proportional to root of k and decreases with increasing mass of the particle. Now we'll take x, displacement and acceleration. What is acceleration? We know acceleration, it is d2x by dt square. That is acceleration. So if we differentiate twice this, we will get a is equal to minus a omega square sine omega t plus phi. So I can write a is equal to a max sine omega t plus phi, where a max is maximum acceleration and small a is amplitude. So for phi is equal to pi by 2, we will have displacement graph like this. We have already seen. And acceleration graph, it is like this. Opposite, because here we have minus sign. Minus sign. So when x is positive, acceleration is negative. When x is negative, acceleration is positive. So on this axis, we will plot a and x for comparison. And now if we see acceleration peak to displacement peak, angular difference is pi, so that is also called phase difference. Here also you will get peak to peak, that is pi. The phase difference between acceleration and displacement is pi. It is pi. Now the potential energy. Potential energy V is equal to 1/2 kx square. So, and the kinetic energy is 1/2 mv square. V is velocity. So kinetic energy is 1/2 m omega square a square minus x square, because we know velocity it is what? Omega under root a square minus x square. So here we can write 1/2 m omega square x square also. Why? Because k is equal to m omega square. So the total energy E is equal to k plus V. So if we add this, we will get E is equal to 1/2 m omega square a square. So E is proportional to square of amplitude. And this energy is constant as long as there is no change in amplitude of the spring mass system. So here potential energy changes with position or displacement from equilibrium position, kinetic energy changes. Now here it is a square minus x square. So when x is equal to a, kinetic energy is 0 and potential energy is 1/2 m omega square a square. So like that. So we'll see that comparison. So total energy of the oscillator is constant and proportional to the square of amplitude of oscillations. So if we take here comparison, here I will take small a, small a, small a, that is amplitude. So see here, this dotted line shows you equilibrium position, x is equal to 0. So here it is maximum displacement, that is amplitude a. So what happens here, at t is equal to 0, suppose it starts from this, from x is equal to a. So x is equal to a, their velocity will be 0 because v is equal to omega under root a square minus x square. Kinetic energy will be 0, but potential energy will be 1/2 m omega square a square, because we have seen these equations, from these equations. And when we release this, here means when it is moving along this direction, means it is moving along negative x-axis. Time will be t by 4, 1/4 of periodic time. Position will become 0 here. Velocity will be minus a omega because it is moving along negative axis. Here kinetic energy is maximum. Potential energy is 0, but total energy is constant. When it comes here at x is equal to minus a after t by 2 time, x will be minus a, velocity will be 0, kinetic energy will be 0, potential energy will be maximum, and that is equal to total energy. Now when it returns, it will again come at equilibrium position after 3t by 2. So position becomes 0, velocity is now here a omega because it is moving along positive x-axis. So see here comparison. They are equal but opposite in direction. Then here kinetic energy is maximum at equilibrium position, and it is potential energy is 0. And when it is displaced, what happens? Towards equilibrium position again after time t, x will be a, v will be 0, ke will be 0, potential energy will be maximum, and total energy is constant. So if we see here comparison, now we know potential energy Pe or V, it is 1 half m omega square x square. Kinetic energy, it is 1 half m omega square a square minus x square. A is amplitude. So suppose we take particle, and these are extreme positions plus a and minus a. That blue ball is particle. So what happens? This is potential energy curve from this, and this one is kinetic energy curve. Now if we see here, potential energy goes on increasing on both sides from equilibrium position parabolically, and it is minimum at equilibrium position, that is x is equal to 0. While kinetic energy is maximum at equilibrium position, and it goes on decreasing on both sides. But total energy E is equal to 1 half m omega square a square, that is constant. So total energy is conserved. So when particle is moving, along the path between plus a and minus a, you will observe change in kinetic energy, change in potential energy. When particle goes away from equilibrium position to extreme position, kinetic energy goes on decreasing, potential energy goes on increasing, means there is interconversion because total energy is constant. So kinetic energy goes on converting into potential energy. At extreme position, whole kinetic energy is converted into potential energy, so it returns. And when it goes towards equilibrium position, its kinetic energy goes on increasing, potential energy goes on decreasing, and at equilibrium position kinetic energy is maximum, so velocity is also maximum. Now if you see that blue ball, it is moving, it is oscillating, and green and red balls, that are changing kinetic and potential energies. So if you see that blue ball, it is oscillating. If it comes at equilibrium position, it moves faster, and when it goes towards extreme position, you will see it slows down. So at plus a or minus a, particle stops momentarily. Means this plus a, it is called instantaneous stop. Instantaneous stop means it stops for a moment and immediately it returns. Means it will not stop for 1 second, 0.1 second or 0.01 second, like that. Its velocity becomes 0 and immediately it returns. So plus a and minus a, these are called instantaneous stops. And along the path there is continuous interconversion between kinetic energy and potential energy. So at some position here along the path, your kinetic energy will be equal to potential energy. And what is that position? So we can get that position here, and that comes out to be a upon root 2 or minus a upon root 2. So you have to simply take 1 half m omega square x square is equal to 1 half m omega square a square minus x square, because they are equal at these two positions, and find here. So 1 half m omega square will go. So x square is equal to a square minus x square. So a square is equal to 2x square. So x square is equal to a square by 2. So x is equal to a upon root 2, that is plus or minus. So plus means here, minus means here. So these are two positions at which kinetic energies and potential energies are equal. Now if we see x is equal to a sin omega t plus phi, v is equal to 1 half kx square. So you can use this sin omega t plus phi here, and this sin omega t plus phi here. So with time x is changing, so v is changing and k is changing. Potential energy is changing, kinetic energy is changing. So you can plot graph of kinetic energy versus time, potential energy versus time, and position versus time. We have already seen graph for kinetic energy, position versus time. This is for phi is equal to pi by 2 I have taken. You can take for phi is equal to 0 also. So this is for pi by 2. So see here. So here below I have shown kinetic energy and potential energy. Total energy is constant. So when particle is moving, its kinetic energy is changing, potential energy is changing, and so on. So this graph, it is for kinetic energy, this graph it is for potential energy. And on omega t axis we will compare them. Now see here, if we take this one, this is one cycle of oscillation, having angular frequency omega, and we can write omega is equal to 2 pi nu. I have taken f, in place of f I will take here nu. Nu is frequency. So for one cycle of oscillations, see here, if we compare this with kinetic energy and potential energy, you will observe here, see how many cycles. So here first cycle of potential energy and second cycle of potential energy, or first cycle of kinetic energy and second cycle of kinetic energy. So you will get two cycles. So for one displacement cycle, you will get two cycles of kinetic energies and potential energy. So for one cycle of oscillation of particle, there are two cycles of kinetic energy and potential energy. Thus the frequency of kinetic energy or potential energy is 2 nu, where nu is frequency of oscillations. So frequency of oscillation of kinetic energy and potential energy, it is twice of frequency of oscillations. So here this is some introduction about oscillatory motion. Now we'll see some multiple choice questions today and some multiple choice questions in tomorrow's lecture on the basis of this theory. Then we'll go for composition of two SHMs and angular simple harmonic motions. So we'll go for multiple choice questions. Okay, screen is visible to you? Is it visible?
Yes, sir.
Yes. Okay, so we'll see some multiple choice questions today. And here, these are best, means these are useful for IIT JAM physics as well as other examinations also. So we'll go to first one. The equation of displacement of particle performing SHM is x is equal to 0.25 sine in bracket 200t in SI units. The maximum velocity is 100 meter per second, 200 meter per second, 50 meter per second, and 150 meter per second. Now we know here, x is equal to a sine omega t plus phi. This is general equation of simple harmonic motion. And what is velocity? Velocity we have seen already. Omega under root a square minus x square. And V max is equal to plus or minus a omega at x is equal to 0. We have already seen this in our theory. So Vmax is a into omega. So if we know omega and if we know a, we can find Vmax. Now here, this is given equation. This is given equation. And what is given equation? X is equal to 0.25 sine 200t. Now we have to compare with this x is equal to a sine omega t plus phi. So I can write this as 0.25 sine omega 200 t plus 0 degree or 0 radians. So what happens here? Phi is 0. What is a? A is 0.25 meter because it is given in SI unit. So A is amplitude, that is in meter. And what is omega? 200t. Here we have omega t. So by comparison we get omega is equal to 200. This is radians per second. Now what is Vmax? Vmax is a omega. So it is 0.25 into 200. So it comes out to be 0.25 into 200 is how much? It is 50. Now meter per second. This is maximum velocity. So out of these 4 alternatives, this third one is correct. C is correct. Now next one. A particle executing a vibratory motion while passing through the equilibrium position, the position has. So we have 4 alternatives. Maximum PE, maximum KE at mean position. Mean position means equilibrium position. Maximum KE, minimum PE. KE and PE both maximum and PE and KE both minimum. We know kinetic energy, it is equal to 1/2 m omega square a square minus x square, and potential energy is equal to 1/2 m omega square x square. Now we know particle, it varies between plus a and minus a through 0. So at this position x is equal to 0. So if you see here, you will get kinetic energy 1/2 m omega square a square and potential energy 0, and that is minimum. Here we have x square. So if x is negative, potential energy is positive. Similarly, kinetic energy, it is always positive. So minimum value is 0 and maximum value is this one. So at equilibrium position. So at equilibrium position, maximum kinetic energy and minimum potential energy. So this second one is correct. Second one is correct. Now we'll go to this third one. The kinetic energy of particle executing SHM is 16 joules when it is at its mean position. if the mass of the particle is 0.32 kg, then what is the maximum velocity of the particle? So 5 meter per second, 15 meter per second, 10 meter per second, 20 meter per second. Now see, we must know formulas. Ke is equal to 1 half m omega square a square minus x square, and velocity is what? Omega under root a square minus x square. These are general formulas. So here at mean position means at x is equal to 0, kinetic energy, that is 1 half m omega square a square, and this is maximum, and velocity is a omega. I have taken here magnitude. It may be positive, it may be negative. But what is given? Kinetic energy at mean position is given, and that is 60. So we will get here 1 half m omega square a square is equal to 60. It is given. And what is mass? Mass is 0.32 kg. So I can write 1 half into 0.32 omega square a square is equal to 60. So I can write here omega square a square is equal to 16 into 2 divided by 0.32. So this comes out to be 100. 32 by 0.32. So omega square a square is 100. So what is a omega? A omega will get 10. So it is 10 meter per second. So velocity is a omega. So it is 10 meter per second. So here third one is correct. Third one is correct. Now next one. Particle moves from the extreme position to equilibrium position. It's first one, kinetic energy increases, potential energy decreases. Kinetic energy decreases, potential increases, both remains constant. Potential energy becomes 0 and kinetic energy remains constant. आता इथे काय दिले? It moves from extreme position to mean position. We have already seen graph. So if we see here x, here 0, here minus a to plus a, we know this is graph for potential energy, and this one is graph for kinetic energy. Kinetic energy. This is for potential energy, and total energy is constant. E is constant. So what happens here? This is extreme position. This is extreme position. So when particle goes from extreme position to equilibrium position, what happens? Kinetic energy goes on increasing, while potential energy goes on decreasing. So kinetic energy increases, potential energy here there must be decreases. So this one is correct, because here kinetic energy decreases, potential energy increases. This is not correct from extreme position to mean position. But if it is from mean position to extreme position, then kinetic energy will decrease, potential energy will decrease. Both remains constant. This is not correct. Potential energy becomes 0 and kinetic energy remains constant. This is also not correct. Now we'll go to next one. We'll go to next one. A particle is executing simple harmonic motion with an amplitude A. When its kinetic energy is equal to its potential energy, its distance from the equilibrium position is, we have already seen, kinetic energy, that is 1 half m omega square a square minus x square, and we have to equate this equal to potential energy. So we get here x square is equal to a square minus x square. So we'll get 2x square is equal to a square. So x square is equal to a square by 2. So x is equal to a upon root 2 plus or minus. So here a upon root 2. This is correct. Now next one, if this is simple one, if velocity of body is half the maximum velocity, then what is the distance from the equilibrium position in terms of amplitude a? So a is root 3 by 2a, b is 2a, c is a, d is a upon root 2. Now we know velocity is omega under root a square minus x square, and V max is equal to a omega. And what is given? Velocity of body is half the maximum velocity at certain position. Then what is the distance from mean position? So we will take this V as V max by 2 omega under root a square minus x square for certain value of x. So it is a omega by 2 is equal to omega under root a square minus x square. So here you will get a by 2 is equal to root of a square minus x square. So a square by 4 is equal to a square minus x square. So here we will get x square is equal to a square minus a square by 4. So it is 3 a square by 4. So x is equal to plus or minus root 3 by 2a. So this first one is correct. This first one is correct. Now we'll see this one and then we'll stop, and remaining questions will cover in next lecture. The motion of particle executing simple harmonic motion is given by x is equal to 0.01 sine 100 pi in bracket t plus 0.05, where x is in meters, t in seconds, the period of oscillation time period in second each. So a is equal to this, b is equal to this, d is equal to this, c is equal to this. So we know x is equal to a sine omega t plus phi, and what is given value? 0.01 sine 100 pi in bracket t plus 0.05. So we can write this as 0.01 sine now in bracket 100 pi t plus 0.05, so you will get 5 pi. So this is omega t. So omega is equal to 100 pi and t is equal to what? 2 pi upon omega. So 2 pi upon 100. So 100 pi. So you'll get 2 by 100. So it is 1 by 50. So it is 0.02 second. So this second one is correct. So now we'll stop here. Thanks very much. And remaining questions we'll see in next lecture. So thanks very much.